Morning.
Like I didn't.
The solar panels for your house thing. I didn't do it.
Yeah, me too. I didn't do anything, so I didn't do it. I didn't do this. The other notes? Wait. What notes? Oh. I thought they were due today.
Did you do one?
Yeah, I already did.
Really? It's you stylish.
They're not due today? Stylish? Show off.
Go get it.
Go get her. Try her.
Do you want
Oh. Well, that's fine.
I gotta get on those tonight. So
They're not awful, honestly. It's like maybe 9-2. Pretty good. It's like 9 pages maybe, but like that doesn't take long either. It's like 30 minutes to finish. 4 pages, right? So 4.5 pages. The Vikings phone?
No, the baseball game.
Oh. Was it a good game?
We're taking 11.
He's still up. Blake.
I don't keep up with baseball.
How's it going? For today.
Cooper.
Is everybody saying the Astros?
I'm
Are they ever stop?
Oh, good.
I'm doing all the players,
Everyone, yeah.
but not went out through they still.
You still have one.
Should make this easy.
Good.
You see
All the teams cheated.
Is he like sick?
He won MVP what year? Stays the Cleveland. Where's Blake at? We better pull up.
Williams out here with me. Maddox. Baker. Blake.
Can't wait to have Mr. Morton's class again today. I was really missing it.
He's so excited.
Yeah.
How come y'all didn't win tennis?
Sorry?
How come y'all didn't win in tennis?
Yeah.
I don't know. Yeah. I don't have a good answer.
You guys got all that school business and then you didn't even win.
Yeah. Mr. Morton was sad too. Not sad, mad.
Disappointed.
Disappointed. She's disappointed. Mr. is disappointed. Rudy's disappointed. He's not disappointed. Mr. Howard, disappointed.
All right. Good morning. Oh.
Good morning,
That
everyone.
sounds good.
Today is Tuesday, October 24th, 2023. Would you please join me in a minute of silence? Please stand if you are able and join me in the pledge. I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation under God, indivisible, with liberty and justice for all. Thank you and have a great day.
Do we normally do the pledge on B-days? I just don't
Like
remember.
occasionally.
All right, so last time I saw you guys, we finished up Unit 3 with the test. And so I'd like to take just a minute and kind of just do a quick semester overhaul because the rest of the semester will go pretty quickly. We've got about 4 weeks, I think, including this week till Thanksgiving break. And then when you come back from Thanksgiving break, I think there's 2 weeks, 2 days, and then a couple days for finals. So semester will wrap up pretty quickly. For our course, our Unit 4 test will include something called the first derivative test, second derivative test, extreme value theorem and mean value theorem. That'll make up Unit 4. Then we'll test on that, and then we do something called curve sketching, which is a lot of the same stuff, just putting it to a graph as Unit 4. Then we'll test on that, and then we usually do 2 or 3 just one-day lessons, maybe a short quiz, and then we'll move into semester exam review. So it'll go by pretty quickly. But for Unit 4, the stuff we're talking about today is not going to just help you with your Unit 4 exam. Again, it's going to carry over to curve sketching, and once we're done with curve sketching, you're going to be close to the semester exam anyway, so this stuff will be on there as well. So I think you'll think this stuff is a little bit easier. The algebra is a little easier. The calculus is a little easier. The calculus parts are mostly things you've already heard before. You just haven't had to go as deeply on the thought process with them yet. But anyway, so our plan this morning is we're going to take these first derivative notes, and then I've got like 11 question book assignment. And so I'll give you some class time on that, but once it looks like at least half the class is finished, we'll move on and take the other notes, and then you guys can finish that up for homework if you weren't in the quicker half of class. Okay, so first derivative test. The first part of the derivative test is something that I'd hope you would already know, but we'll see if it jumps out at you. If your derivative is positive, what do you think that means about the function? I'm sorry, one more time? That's correct. Remember, derivative is just like slope. So if the slope is positive, your function is going up. If your slope is negative, your derivative is negative, then your graph is going down, decreasing. And if your derivative is 0, then at that instant, it would be constant. So just one little parabola, and we can draw in all of these things here. So if this guy was the function, I would know during this time his derivative is positive because of positive slope. During this time, his derivative is negative because of negative slope. And then at this one instant at the top, the derivative would be 0 because the slope at that instant is 0. So again, you've already been thinking of derivative as slope, so this questions 1, 2, and 3 should not feel like much of a stretch. Okay, there is another term that we're going to be using the rest of the year now. It's called critical numbers. And critical numbers are any numbers that make the first derivative equal to 0, which is what happens 95% of the time. But also if it makes the first derivative undefined. So I'll have to say that every time so that you don't forget that, because you still get tested on this. Now I probably should have printed this on our notes here, but let's go ahead and squeeze this in. You need to know the difference between a critical number and a critical point. A critical point is just going to be a critical number that is a point on the graph. So x equals 3 might be a critical number if it makes the first derivative 0 or undefined, but if x equals 3 doesn't exist on the graph, it can't be a critical point. If it's not a point on the graph, it can't be a critical point. Okay, and what we care about critical numbers for is that they often, it's not a guarantee, but they often tell us where the extrema are. So remember, extrema are like relative maxes and relative mins. So the next little section of our notes here, we're going to go through all 3 possibilities. So sometimes it'll just be, now these equations I put on our notes here are just pretty basic, but it gets the point across. Sometimes you're just asked, what are the critical numbers? So you have to, or critical points. So you would have to know that is when the first derivative is 0 or undefined. So you'll have to take the derivative. If there's ever an x in your denominator, you need to figure out what numbers make you divide by 0, because that would be the undefined part. But most of the time, it's just when the first derivative equals 0. So at x equals 0, I know it's got a horizontal tangent line. Horizontal tangent line is the only place, critical numbers are the only place that your graph might be changing directions. Now, the reason why I like to use a really basic function here is because you should know what this looks like. And we can visualize. X equals 0 was not a relative max nor a relative min. X equals 0 is still a critical number though. Technically, it's a critical point as well, because 0, you can plug 0 into the original function and get a point. So if you want to call it a critical number or a critical point, it's fine. Okay, so again, the main use of critical numbers is to find relative extrema, but not all critical numbers give you a relative extrema. So I'm starting off with that example so you don't ingrain that assumption in your head. So what the first derivative test actually says is that if your derivative changes from positive from one side of something to negative on the other side, well, when f is positive, we know the graph is increasing, and then when f prime is negative, we know the graph is decreasing. So that guarantees us that we would have a local or relative max. Local max and relative max, same thing. Local and relative are interchangeable. So again, pretty easy function, but some of your test questions the rest of the semester will be find the critical numbers. So you would need to know critical numbers are numbers that make the first derivative 0 or undefined. That's a critical number. So if you're just asked for a critical number or a critical point, you're pretty much done. But most of the time, you're asked to find relative extrema. So I would like to know where the local max or local min are in these questions. So in calculus, we have this thing called a line chart, and you need to make sure you put this on your notes, and you need to start making a habit out of doing these. This is really important for FRQs. But if you know where all the critical numbers are, we can put those on a line chart and label it as a critical number. You can just put C over N for critical number. And assuming I don't know what this graph looks like, assuming that this directions didn't tell me kind of what it looks like, what you need to do is you need to try values around each critical number. So I need to plug in some number to the right of 0 into the first derivative. So you can pick 1 if you want, you can pick a half if you want. A half sounds a little bit harder to deal with. You could pick a million if you want. That sounds harder too. I'm just going to pick a number that's as easy to work with as I can, like maybe 1. And honestly, I don't even really care what the derivative is at 1. I just care if it's positive or negative. So you should have the first derivative over here. If I plug this into the first derivative, this would be negative, so I know the graph's going down. So we draw just a visual that we know the graph's going down during that time. But I also have to test to the left of each critical number too. So this was negative, that's why it's going down. Okay, and then test to the left of the critical number. So if I plug -1 into the derivative, I get +2. Again, I could really care less about the 2, I just care that he is positive, because when the first derivative is positive, that's like the slope is being positive, so the graph is increasing there. So this is nowhere near what the function looks like, but it tells me the direction of the function. Now once again, I picked out a function that I think we should all know what it looks like. It's going to look like x squared flipped over the x-axis and shifted up 7. And of course, normally you don't know what the graph looks like, but this is a very simplified version of what this looks like. It's increasing from -infinity to 0, just like this shows, and then it's decreasing from 0 to infinity like this shows. So this line chart is a good way to show your reasoning. So if the question was to find the relative extrema, I can see right here it was going up and then down. So at x equals 0, there is a guaranteed relative max or local max. Okay, so either your critical numbers don't give you relative extrema, or your critical numbers could give you a relative max if your graph's going from increasing right before it to decreasing right after it. And then if your derivative changes from negative to positive, so your graph goes from going down to going up, that would be a local min. So the calculus way to do this, well, I guess we'll do it backwards this time. We'll do the algebra way. So you did the same thing in Algebra 2. Most of the time you had a calculator, or the teacher just gave the graph to you, and you were asked to identify local maxes or local mins. So you could just look at the graph and say, okay, it's right there. We're doing the same thing with calculus, so we don't need to know what this function looks like. The function could be much more complicated, but we know the only place it might be changing direction is at critical numbers. And critical numbers occur when the first derivative is 0 or undefined. So x equals 0 is the only critical number. We organize our information in this line chart. So don't just put x equals 0 here. You need to state that you're putting it on there because you think it's a critical number. And again, critical numbers are the only place that it might be changing direction. So as long as I test one point to the right, whatever it's doing at 1 is going to do at 2, 3, 5, 10, 100. It's never going to change directions because there was only this one critical number. So you plug in a number into the first derivative, I get something positive, so I know it's increasing there. First derivative is positive, so increasing. But I also need to test over here, because if this is positive, then this is not a relative extrema. Increasing followed by increasing is not an extrema. So I need to plug in any number to the left of 0, like maybe -1. Plug it into the first derivative to see that the first derivative at -1 is negative, which means our graph is decreasing. Now, with certainty, I can say if it goes from decreasing to increasing, this right here is a local min. Same as this visual over here. But again, normally you don't have the graph in front of you, so you can't just get the answer that way. We got to do it this way. Now again, of course, there's a handful of things that you got to practice to make sure that you know them, but taking the first derivative shouldn't be an issue. The algebra is solving for where it equals 0. Most of the time it's not too messy. This line chart's not too hard to make. The idea of it going increasing versus decreasing, whether your first derivative is positive or negative, it's not too much of a stretch from what you already knew. So that's why I said I think this section's a little bit easier. Okay, and then last one, if it doesn't change size. So that was like the x cubed that we looked at before. If it goes from increasing to 0 to increasing, that is not a local max nor a local min. It has to change signs. A local min is where it goes from decreasing to increasing. A local max is where it goes from increasing to decreasing. But if it's not switching, then it doesn't create a local max or a local min. Okay, I've got a couple questions on here to practice so just two, and then this is similar to what you guys will be practicing in the book in just a second. Before I do these two practice questions, though, we kind of get to the point in the year where we get to FRQs, and students like to use the word it in FRQs, and so I have to say this to you guys at some point so that you slowly start to stop doing that. In the FRQ, if you say it was positive, or it is increasing, or it is bigger than that, you can't use the word it because nobody can assume what you're talking about. If you mean the function is increasing, say the function. If you think the derivative is positive, say the derivative is positive. But you should not be using a generic word like it. I can't make an assumption about what you're talking about, nor will the AP graders make an assumption. All right, so question 4, find the local extreme points of this. So basically, tell me where the max and mins occur. So we don't have a calculator. I don't know what this graph looks like, but I know the only places it might be changing directions is at critical numbers. So I would take the first derivative, figure out where the first derivative is 0 or undefined, so there's going to be some algebra work, but looks like a -2 and 2, and then 3 doesn't equal 0. So there's two numbers that are considered critical numbers. So this graph might change directions at 2, and he might change directions at -2. Doesn't mean he has to, but he might. Now I just basically need to know what's going on around those critical numbers. Because if I know if it's increasing or decreasing here, I know it's going to be increasing or decreasing this whole time. Because critical numbers are the only place it can change direction. So I simply need to pick a number between 0 and 2. Anything you want. 0 is a nice one. And plug that into the first derivative. Now, you guys have to show all of this. If you just say x equals 0, and then all of a sudden you do this or this, you're not showing why you think it's increasing or decreasing. You need to show, I'm plugging 0 into the first derivative, and that would give me something negative. -12, but again, I don't really even care that it's -12, I just care that it's negative. So it's decreasing this whole time. Now, what you should not assume, even though this happens more times than not, is you should not assume, okay, well, if it's going down here, it's probably going up here, so this is probably a min. And if it's going up here, it's probably going down here, it's probably going up here, and this is probably a max. You should not be assuming any of this. You can actually test it. Just plug in a number to the left of -2, like -3 into the first derivative. That gives me something positive, so he's increasing, and a number to the right of +2, like maybe +3. That is positive as well, so increasing. All of that, so I have this visual, and now I can see it goes from increasing to decreasing at -2, so this would be a relative max. And it goes from decreasing to increasing at +2, so this would be a relative min. I don't need a calculator. I don't have to have the graph provided for me like Algebra 2. We can figure out when it's increasing or decreasing and give ourselves a nice little visual so that we are sure that we've got that correct. Okay, any specific questions about 4 before we look at one more? Okay, This one is probably a little closer to what you would see on the test, just because this one's a little messier to work with. But again, the process is still going to be the same. I'm still going to find the critical numbers. I'm going to still test around the critical numbers to know when it's increasing and decreasing. And if I can see where it's increasing and decreasing, I can point out where there's relative maxes and relative mins. I guess what would make number 5 a little harder is that the first derivative is a little messier. We'd have to do power rule, bring the power down, lower the power by 1, and do chain rule. So this is like 4x over. So the first derivative is a tiny bit harder, but not harder than what you've had to do earlier this year.
Can you simplify it for you to
What would simplify?
you put the multiply 2x by 2
And-
and you the 1/3 in the denominator.
Well, my 1/3 is in the denominator,
I just wanted,
and my 2x times 2 is 4x. I already did that.
I was wondering if you didn't have to do that.
I don't know. I don't know that you have to, but it's probably a good idea usually. Okay, so now, if critical numbers come when the first derivative equals 0 or undefined, when does a fraction equal 0? Okay, so there's a critical number at x equals 0, because that makes the numerator 0, and 0 divided by anything is 0. How do you make a fraction be undefined? When the denominator equals 0. And again, this is the first question where we even needed to worry about where the first derivative is undefined, but you have to consider it every question. I know it's usually when it's equals 0, but also when it's undefined. We could divide both sides by 3, we could cube both sides to get to this, and then we could factor to see that 3 and -3 are also critical numbers. Now, sometimes, even on your AP test, you should probably have at least one question where all they ask you to do is find the critical numbers, and you can quit. So we'll probably do the same thing. 1 or 2 questions on your next test will probably just be find the critical numbers. But the reason why we care about critical numbers is that these are the only places that the graph might change direction. So for my line chart, I'm going to have to test around 0, around -3, and around +3. Those are the 3 times it might change direction. So, to know what's going on between 0 and 3, I need to plug in a number into the first derivative, like maybe 1 or 2 or 1/2 if you really want, but pick something easy. Okay, here's my first derivative, and again, I don't care what the number is, I just care if it's positive or negative. So if I plug a 1 in here, the numerator is positive, but the denominator is negative. A positive divided by a negative is a negative. When the first derivative is negative, the function is decreasing. Okay, to figure out which direction the graph's going between -3 and 0, I will just do a test point between those, like maybe -1. So at -1, the first derivative, the numerator's negative, the denominator's negative. Negative divided by negative is positive. Again, I don't even care what the value is, just whether it's positive or negative. That's why I'm not having to be super careful about my arithmetic. So already I can tell that there's a relative max right here because the graph was going up and then it starts going down. So at x equals 0, we have a relative or local max, whatever you want to call it. But -3 might be a min, and 3 might be a min. So we also have to test around these as well. So let's maybe throw in -4 into the first derivative. That would give me a negative over a positive, which would be negative. Which means that now I can say with confidence that x equals -3 is a relative or local min, because it was going down and then up. And then finally, test to the right of x equals 3. Maybe throw in 4 into the first derivative. That would give me a positive over a positive, which is positive. When the first derivative is positive, your graph's increasing. And now that I'm sure it was decreasing and then increasing, at x equals 3, I have a relative / local min. Now, before we totally put this aside, I do want to just graph this one real quick, just to convince you and help identify what it is we just did. Okay, so we're saying there should be a min at -3 and +3 and a max at 0. So here's the original function. There should be a relative min at -3, at +3, and a relative max at 0. So that calculus doesn't help me determine the shape of the graph or anything, but it does help me find these relative maxes and mins. And it's not much different than you've already done. Okay, any immediate questions about number 5? Anything I went over too quickly there? Okay, then you need to try it out and see how you do. So I've got a short book assignment, so if you please do this on a new piece of paper. And as I said at the start of class, I'm going to give you some class time to work on this, but maybe not enough time to finish it. It just depends on how quickly you work. So my goal here is to go around and help people, and when it looks like about half of the class is finished with the book work, we will start the other handouts. We won't finish the other handouts, but if you're in the quicker half of the class that's working, I guess you won't end up with homework, and if you're in the slower half, you might have to do a few for homework.
Can I ask this question?
Yeah, you can help yourself. You don't have to ask. As you can probably guess, when we get to the second derivative test is going to give us different information about the function. So it's good to make sure that you really fully understand how we're using the first derivative test to keep those separate. If you didn't pick up a book on the way in, you need to go get one.
There's more books over there last night.
Oh, I'm sorry, they're out of books.
There's one.
Does anybody else need a book? I have extras on the back of it.
Oh, yeah, but like, what about?
Well, what is is this the same thing as a
Yeah.
Simplify it. You have to put it over 16.
What does mean? Oh, because it's times 0.
I'm a pin girl, so it's possible I won't. If it works.
Yeah.
Yeah, that makes sense.
You have any questions, Joe? Algebraically, it's- First, check your answers that you guys worked through here, so you don't have to go back and redo a bunch.
From what, I just started.
Is that okay?
Yeah, I'm not sure, yeah.
I think I screwed up just that one.
What was the function originally? That's good. Okay. Well, yeah, but you're multiplying this by 4, and then, yeah, you gotta multiply this by 4 too, don't you? All or none. I don't know what's that. We're increasing or decreasing. So you should have. I don't see where your answer is. So like on number 3, you spelled it out this way. Do the same thing now.
But yeah, so I'm getting like local min or local max. How do I like put that like increasing, decreasing?
Well, this starts increasing at 3, and then it goes forever to the right. So you could say increasing from 3 to infinity,
Okay.
and decreasing from negative infinity to 3.
girlfriend that you both get around? I have bus duty on Monday and Wednesday, so I will see you.
Is it negative one?
Yeah.
No, I did all the system, so it'd be the same thing, yeah. Divide and that's still 0, and if you take the square root,
Oh, it's still 0.
yeah, 0.
Again, please call me over and let me help you get unstuck. First question you get stuck on, you're gonna have the same issue on a later question anyway, so. But if you can do the first few, you really should probably be able to do all of these. All that gets harder, well, actually, I take that back. The last couple questions, you're trying to do it in reverse, I think, but. The only thing that can be harder about these are harder first derivatives and harder algebra to solve where it's 0 or undefined. But the process for finding critical numbers, doing a line chart, looking at the line chart to know increasing, decreasing intervals, and local max and mins is always going to be the same. So
I got one. Bread and chocolate.
No.
okay.
How do you plug it in? Plug in 0, plug in 1.
Wait,
So
how
what
do
is
you,
the negative
how do you
value
change this?
that it is?
How do you square it? So you have to square it?
0,
0.
Because you get like a fraction.
So 16.
So I think it's just 1. Because it'd be 1 and 15. So that should be negative 2.
So that it's just increase from negative 2 to the
We're stuck on number 1. Okay, so we thought it'd be like something to do with like -4, 4, and 0.
Okay.
When you look at the answers, it's like -2 squared to 2,
Oh,
and
nine, it's
2
a-
squared to 4. I'm
Mm,
not sure how we.
Yes.
your derivatives wrong. You have to do product rule on that derivative. X times the square root of something. You don't get to
So right
do-
here? Or wait.
From here to here.
Okay.
Well, actually, these are the same case, so from here to here.
Okay.
You gotta take the derivative of x with the square root stuff left alone, plus x left alone times square root of the square root stuff.
Alright.
So I should write this one. if you're struggling to get the right answer on number 11, you need to make sure that you did the product rule for the derivative. It was x times the square root of 16 minus x squared. You have to do product rule to get the correct derivative. You can't just take the derivatives individually and slap a multiplication sign in between.
Did it go?
The derivative is negative x squared over square root of 16.
You're on the right track if you don't have the quite the same. Well, this, okay, it looks like you multiplied the numerator by the same square root.
Oh.
Square root of something times square root of something gives you that.
Yeah.
But you didn't multiply the denominator by that. He had a denominator of 1, so it shouldn't be 1 anymore. And then the right fraction, I don't think you need to multiply it by anything, because it already has the right common denominator. Yeah.
On this one, where would, I'm trying to set it equal to 0, so is this one where it's like try to get the numerator and the denominator equal to 0?
If it's one big fraction, is it one big fraction yet?
No.
Okay. how
Because
could-
then if you multiply this by that, then the square root goes away.
Okay, what can you do to make it one big fraction? Very good. Common denominator. So the common denominator will be that, correct? The right fraction already has that as a denominator, so you shouldn't be multiplying the right fraction by anything. But the left fraction, you need to multiply the top and the bottom by that. And the square root of 16 minus x squared times the square root of 16 minus x squared, it's going to be 16 minus x squared.
Which is 16.
Now that it's one big fraction, you can know that all of this equals 0 when the numerator equals 0, and it's undefined when the denominator equals 0. But you can only do that trick if it's a big fraction,
Okay.
not if there's multiple terms.
Sorry.
Where'd you get print? Are you saying the top and the bottom equal 0? Or how do you do it? Okay, I didn't do it. It's like it was good to do. Yeah. Yeah. It's just doesn't equal 0. So you have to find it has to equal this equal to 0. How do you solve that right there?
Okay, I went a little further on number 11 on the board, mainly because there's one algebra thing in here that I'm afraid you're going to forget. I see, the first derivative would be 0, since I've got it written as a whole fraction when the numerator equals 0. So subtracted the 16 over, divided both sides by -2, took the square root of both sides. So undefined when the denominator equals 0, so I set the denominator equal to 0, squared both sides, subtracted a 16, multiplied both sides by 16, and then took the square root of both sides. What did I forget? Right, when you do the square root of both sides, it is plus or minus. Number 11 doesn't have 2 critical numbers, it has 4 critical numbers. And that can add a lot of confusion if you forget that algebra step. Okay, I wanted to say one more thing real quick about number 11. So, I already mentioned that it had 4 critical numbers. So your work could look quite a bit different if you thought there was only 2. But what happens when you try to test a number to the right of 4, like 5? If I plug 5 into the numerator, I get something negative. What about 16 minus 25? Okay, 16 minus 25 would be negative what? Okay, and then the square root of a negative number is, okay, well, where do imaginary numbers show up on our graph? They don't. So x equals 5 does not even exist on this graph. If it has no slope, then either it's vertical, which means it's not a function and it was a function, or it doesn't exist there. If you do the same thing with -5, you also get an imaginary number. And I just wanted to point this out because I wanted to graph it real quick for you. So you can see that when you plug in a number and you try to take the square root of a negative number, it could be that you have a mistake, or when you graph it, it could be just that the graph doesn't exist after 5 or before -5. But negative till, or decreasing till -2 square roots of 2, increasing from -2 square roots of 2 to +2 square roots of 2, and then back to decreasing from 2 square roots of 2 to 4. So when you try to plug in a number bigger than 4 or less than -4, that doesn't make sense, and the reason is the graph doesn't exist there. Possibly, but you're assuming this A value is 1, and like this parabola could be like, this could be A is 1, and it might actually just be like, swipe it off. You don't need to try to come up with the function at all. They want you to try to graph the derivative. So if you know what the function looks like, we should know a lot about what the derivative looks like. So for example, so this is trying to work it backwards basically. When is the function, when is the function increasing?
Negative or
Is it, wait, visual? Is it something?
And decreasing from negative infinity to 2?
Yes.
Okay, well when the function's increasing, what does that tell you about the derivative?
It's increasing?
If the function's increasing, the derivative is positive.
Mm-hmm.
If the function's decreasing,
the derivative is negative, right? So if you need to graph the derivative, you know that he is he's positive from 2 to infinity. Positive means above the x-axis. And he's negative from negative infinity to 2. And negative means below the x-axis.
So it's not like exact or anything, it's just like a rough.
Yeah, like, I mean, I don't know, like, the steepness of this.
Okay.
And on the next questions, like, you'll know it goes up to during this time and down during this time, but you don't know, like, what y value it goes to and what y value it comes down to.
Okay.
Once you get that specific, that's what we call curve sketching, and that's the unit after this. But all of this stuff still helps us with the curve sketching also because of the graphing. But also, another thing to think about is your function look like a parabola, which is degree 2. So if you think about doing the derivative in the power rule, and the power goes down by 1, the derivative should be a linear function.
We did exactly the same.
You would just.
Oh, yeah, you're right.
Yeah.
No, you're so right.
I know some of you are closer to being finished than others, yet if you end up having time to finish in class, you might want to go ahead and turn it into Google Classroom, because you will need to do that before class on Thursday. And if I end up moving along here and you don't have enough time, then you'll just need to do those last few for homework. But right now, we're going to stay on this. This is not, I don't know what number this is.
Like, it's going crazy on me.
Yeah.
Okay, well that's so they're giving you a picture of the function, and you're trying to come up with a picture of the derivative. So this is kind of backwards from what we're using today. So I just said, if you know what the function
So this
is
is like the first
decreasing
one on the
from
left,
negative
so from
infinity to 2, that means the derivative is negative, or is negative during that time. So my graph up there, from negative infinity to 2, I know the first derivative is negative, so it was below the x-axis. Then it's increasing, which means the derivative is positive. So then I graph the derivative to be positive. Okay.
Well, it's not like a slope, we're looking at the below that x-axis.
I think it also helps if you force yourself to write this out too. If you force yourself to say the function's increasing during this time, decreasing during this time. Increasing means the first derivative is this, decreasing means the first derivative is that. This tells you when your graph should be above the x-axis and below.
Is there gonna be a jump on the graph? Like, how do you get from it being positive?
No, there shouldn't be any jumps. What does it start off with?
Negative infinity to negative 2 is decreasing.
Okay, so that would be,
Below the x-axis.
okay.
And then negative 2 to 0 is increasing.
Okay.
And then 0 to 2 is decreasing.
Okay, so right here, instead of just continually going up,
Oh.
so now it's still positive.
So there can't be jumps.
No, there shouldn't be a jump. And then you said it was negative, and then back to positive, I'm guessing? So just make it curve back, to switch back when you need to. Now again, on this, we're not going deep enough to know like this. I have no idea if it's like short or if it goes really high up, but just an estimate. x equals 1 is a critical number, that's where the first derivative is either 0, so it's not increasing or decreasing, it's flat, or it's undefined, which means it would be vertical or non-existent. You shouldn't be testing the critical numbers, you should be testing the numbers around it.
That should be 2.
Knowing whether the critical number is 0 or undefined is what lets you know that those are critical numbers, but so they're not used to that.
Critical number.
Yes.
Identify the open and non active.
I'll just get the pencil.
Yeah.
What do you want?
We need like the orange one.
What it meant, I guess, was like x is equal to -1 is a local max.
Assuming that if it's really increasing here and then decreasing here, then yeah, that's a max.
But you wouldn't label this anything, right?
It's neither one.
So
Sometimes you'd need to say neither, but
neither.
I have a question. How can we tell where the relative min or max is when it's just like a line?
So the derivative's just
Well, when you say there isn't one,
basically
by the graph.
so
when you say it's just a line on what kind of graph? A function graph, a derivative graph?
The derivative.
Okay, that makes a big
the slope's
difference.
decreasing all the way until
What are you looking at? Part I, 90I?
And then at 2 it's since it's flat, it's gonna be 0, and then since it's increasing,
Okay, this is a first derivative.
so it literally just looks like that.
And you're supposed to graph the function?
So
Okay, so when the first derivative is
until, like,
negative,
1-ish, right?
when the first derivative is negative, what do you know about the function?
So it's decreasing until -2, and then
It's what?
It's
we don't
increasing,
know.
or it's decreasing from -2.
you just know the slope's decreasing.
Okay, so from negative infinity
Not the slope's decreasing, the slope's negative.
to 2, the function
So it's
needs to
gonna
be
negative until
decreasing.
I put 1, so
And then when the first derivative is positive, the
negative
function
2, so it's gonna be
is
0,
increasing.
and then it starts, this thing starts
I don't know, something like that.
having a
Yeah,
positive
it
slope.
doesn't even say we have to
So
graph
this will
it,
go
but I
in
guess that'll help
positive.
us.
Well, even just a quick little sketch is going to help you answer these.
Okay.
Because now I can see it's increasing from 2 to infinity. I can see it's decreasing from negative infinity to 2. I can see that this is a relative min. And I think that's what it's asking for. So
That makes sense.
Yep.
it's not that you can't answer those 3 questions just looking at the graph, but it's hard at this point in the year. I can look at this and see the function's decreasing then increasing, so I know that this is a relative min without piecing it together by graph, but
The next one's 2. 1 and 0.
okay.
Yeah, I was like trying to figure out. So this is how you did this one.
Yeah.
I just like can't figure out.
Well, these are functions, so we're going to think about where it's decreasing or increasing. Because it's decreasing from negative infinity to -1, that means the first derivative would be negative there.
What was your derivative?
So I'll just make a graph where it's below the x-axis until -1.
What's increasing?
Okay. And then
Can't
it's,
read that.
the function's increasing from -1 to 0. And when the function's increasing, the first derivative is positive. So it needs to be above the x-axis from -1 to 0. Okay.
Oh, shoot.
And then it's decreasing from 0 to 1. So that means the derivative should be negative.
Oh.
Wait, now see, yours isn't negative there. Last step, even though it wasn't wrong yet, you need to make it curl back so that it can switch at 0,
Relative minimum.
like this.
So it's decreasing and then
I know.
increasing.
See how it's still positive from
Right.
-2 to 0 or whatever, or -1, whatever it
Decreases
was.
to 2, so 2 is the minimum.
And then the function's decreasing, so the first derivative is negative below the x-axis, and then the function's increasing, which means the first derivative is positive above the x-axis.
Okay, that makes sense.
Decreasing from 0 to
And the
1.
next one.
Yeah. Mr. Townsend, for 90, can you kind of just estimate like where the critical numbers and then the sigma are? Or do we have to come up with the equation for the line?
You certainly don't have to come up with the equation, but I don't think you should be estimating. Like on that one, I could tell that it was switching at x equals 2 from the graph.
Oh.
So that's enough to know. Again, keep in mind that on 90 and what are the other parts? The 77, 78,
Wait. How can we change that?
77, 78,
Doesn't-
and 90. All of these make some pretty rough sketch graphs, and these are good enough for now. When we come back and make them more accurate, that's what's called curve sketching, and that's the next unit. Like on this question, 90, like I knew where it was switching, but I mean, I don't know. It could be like this for all I know. I don't really know what this y value is, but I do know when it's decreasing and increasing. So.
Should we ask about the graph of the
Oh, it's a graph of the
Are you looking at that 9? That's 9 in this is.
Oh, no, that would,
Like
that changes a lot.
Okay, yeah, that
Yeah, I was like, it's just, it's all increasing.
And that kind of goes back to the notes where I said you can't say it is doing something in an FRQ because it makes a big difference. Are you talking about the function or the first
Because
derivative?
on,
Because one
if
can be
it's
right.
0 on the derivative.
We can't just
Because on the normal
assume
part
it's
one,
right.
that would be like when it's 5, you know?
Or the other one y'all do is the graph is increasing.
Yeah.
What graph?
Increasing
The provided graph? That would mean one thing, but y'all don't usually say that.
For graphing f of x, and I have like an increase, how do I make it decrease without making it go back up?
You're on,
Can I make it just go straight back up,
which one do you
even though
want?
it's below the x, like?
Should be
no
2.
idea.
Is it number 2?
Yeah.
Let me look at it a second. Okay, I'm going to estimate that it is crossing at 1, or not crossing at 1, but okay. Did you say x equals 1 is where it switches?
Yes.
Okay, so when the first derivative is positive,
Increases, so that'll be mid.
the function is increasing. So from negative infinity to 0, I know my graph needs to be going up. I don't know how far up it goes or anything, I just know it's going up during this time. You're okay with that? Okay, when the first derivative is negative, the function is decreasing. So from 0 to 2, the graph goes down. And then the function goes back to increasing. So I don't know, something like that.
Yeah, that's what I have.
And again, this is probably not what the graph looks like because I don't really know this y value or this y value. This has probably got some curvature to it. You know, it's probably not sharp turns, but it's more than enough to know, to be able to state that it's increasing from negative infinity to 0 and 2 to infinity, and decreasing from 0 to 2, and to identify x equals 0 is a relative max and x equals 2 is a relative min. So it's just different. Instead of giving you the function, you have to take the derivative, you have to figure out what the critical numbers are, you have to test numbers around the critical numbers to know when the derivative is positive and negative. The graph's giving you all of that. The graph is meant to be easier, you just have to read it a little bit differently. We've got about 7 minutes left, so I guess we're not going to have time to move on and start the next handouts like I wanted to. But 7 minutes, you guys should still keep going here unless you're finished. But at the very least, between now and Thursday, I need you to finish practicing those few book questions. All of those are worked out on the website, so if you get stumped on any, you can watch the couple-minute video to help you get unstuck. And you need to put that in Google Classroom before class starts on Thursday. So, what you didn't get to in class is going to be your homework.